Okay. So, in the beginning, I will start with a short history about software development. I was wondering when this job, I mean the software development job, first appeared. And after that search, I found out that the first software developers were working at the Apollo program. So since then, of course, a lot of new jobs appear. And right now, in our days, there are 21 million developers. In 2013, for example, there were 19 million developers, and according to ADC, in 2025, there will be 25 million developers. So a lot of number of software developers developing software applications, mainly because software application proved to be a good thing. So software applications actually makes our life easier. It automates different activity of our lives. And I was also wondering about the number of these applications. And as usual, I searched on Google. And what I have found out is someone put the same question on Quora. Another one gave him an answer. He estimated the number of near billions of applications. Why? Because there are a lot of industries, a lot of apps, a lot of games. We are spending our daily life using these applications. And the idea is to reduce as much as possible human intervention. You know, we can visualize all these applications as a Maslow pyramid. In the bottom of our pyramid, there is the majority of applications. All of them not doing, let's say, very clever stuff, are just simply helping our daily life. They are doing small computation, small data transformation, data monitoring. But they are important because they automate our daily life. Once we go to the upper level of this pyramid, applications become much more smarter, much more clever. But of course, the number of them decreases. The idea, as I mentioned, is to reduce as much as possible this human intervention. And you know, there are a lot of, I can say, boring activities. For example, registering data, transferring data from one application to the other. Of course, there are a lot of different APIs available, which help us to integrate different applications. But there are also a lot of boring activities. I will start with a short example, which will become our next starting point in our discussion. So suppose you have a CEO called Bob, who actually wants to see a particular report in the middle of the night. What he usually does, he sends an email to his secretary asking for the report. But right now, because we are in the middle of the night, he can't do that. And what's the solution for this particular problem? The solution is RPA. Sorry. The solution is RPA, Robotic Processing Automation. So instead of having Alice in front of the computer, we can design a robot, a software application, which can do exactly what Alice should do. What does it mean? That robot should be able to understand the email sent from Bob. He should be able to open the reporting application. He should be able to generate the corresponding report, and after that, he should be able to send the email back to Bob. But of course, for doing that, our robot needs to be smart enough. And if you are looking back in our pyramid, this robot is in the top of our pyramid because it should be smart enough in order to manage all the other applications. Of course, these robots can work 24 hours per day. They can be scheduled such that they have the maximum productivity. One of the core activity in RPA is to be able to control any other application. This is the fundamental thing that the robot needs to be able to do. And this relates to screen scraping. And of course, for this part, there are two different approaches. The first one, which is always used, is related to accessibility API, which actually what it implies. So once you have to design the application to be accessible. For those who don't know what accessibility means, is designing the application such that is accessible for a person with disability. Of course, there are a lot of features which comes to that. It's also the UI automation feature. So once you make the application accessible, you can have accessibility client application, which based on some kind of protocol. There is a called interface, it's accessible, which allows you to actually remote interact with that application. You're able actually to see what controls are inside the particular screen and how you can interact with those controls. Of course, this is a very, very good approach because it can be done programmatically. But one of the problem with this approach is that there are several scenarios in which you cannot use that. For example, not all control vendors are implementing correctly the accessibility API. Also, for example, there are a lot of old applications which doesn't comply with any accessibility rules. There are also such environments, for example, in a Citrix environment, even if you are designing the application to be accessible, because the application it's virtualized, it's not executing on your machine, you're actually interacting with a series of images, you cannot rely on the accessibility part. And because of that, you should try another approach. And the other approach is to rely on the image itself, to behave exactly like humans do. So to understand for image itself what controls are in the screen and how are you able to interact with them, based on of course, on the keyboard and the mouse. This requires a machine learning approach. We have initially started with a small OpenCV processing application. We actually search for rectangles and circles. We assume that majority of almost all controls are somehow rectangles, but of course not all the rectangles are controls. And in order to classify which is control and which is not, we initially put a support vector machine classifier on top of this rectangles. But it proved to be that this support vector machine classifier was not accurate enough. You know, in this world of image processing or image detection, in image classification, deep learning is the most powerful tools. It actually beats any other approach. So, because of that, we studied what are the best approaches for our problem. And control detection, we are talking about screen scrapping, but control detection, it's related. Control object detection is tackled by deep learning. And there are several architectures which deals with this problem. So there is RCNN, there is fast RCNN, there is faster RCNN, and is YOLO. I will talk about all this convolutional neural network. I will talk about all this neural network architecture used for detection. So let's start with the beginning. The first architecture for detection was RCNN. You actually have a convolutional neural network trained for classification, and you use it for detection. How you do that? So you have a window, a sliding window, and you move your sliding window on your input image, and then you do a classification. So in order to make a detection, you have to do a lot of classification. Of course, this approach is slow. There is also an improvement designed by Microsoft. It's called fast RCNN. The idea is to reduce the number of passes, to your network. So this network is fast RCNN, and what he does in detection. So you have the input image, you pass this image to a serial convolutional layers. In parallel, you have a mathematical algorithm. For this architecture is called selective search. So you apply this mathematical algorithm to the image itself. As a result, you have a series of candidates, region proposals, and those region proposals, together with the output, the projection through the convolutional layers, are passed to a special layer called region of interest pooling layer. And then there is a series of fully connected layers which does the regression and the classification part. So there is a softmax classifier which deals with the classification part, and the regressor for finding the boxes. In terms of performances, it's a huge improvement. Also in accuracy, it's a huge improvement. Now there is also another architecture, also designed by Microsoft, which is quite similar with the fast RCNN. It's the state of the art in terms of accuracy. The single difference with the fast RCNN is that instead of using a mathematical algorithm for doing the region proposal, it actually uses another neural network, a convolutional neural network called RPN, region proposal network, which deals with this problem. The rest is the same. So instead of using a mathematical algorithm, we are using another neural network which deals with this problem of proposing candidates. So those candidates are actually areas in which there is a possibility for an object to exist or not. And the last principal architecture, of course, there are many other architectures, but relies on these four. It's called YOLO, was designed by Facebook. And the idea is you see your image, your input image as a grid. And of course, in that grid, there are grid cells. And each grid cell is responsible for detecting the objects which are inside of the cell. Now, I will talk about some of our approaches for doing this detection. Of course, we tried all these strategies. We used RCNN, we used fast RCNN. We are trying to use also faster. We also use YOLO. We did this implementation in TensorFlow. The problem with YOLO was the fact that it requires a lot of data, and we didn't observe a good accuracy. Now let's talk about one of our approaches. So you have an application screen in which you want to detect different controls. You want to see which are all the controls inside the particular screen, and what are there, which controls, what are the control types, where they are, and what are their content. So first, what we are doing, we are using the Kenny algorithm, which is used for detecting edges. So it's based on some thresholds applied to the gradients. So you can use it. It's very, very fast. You can use it to detect which pixel is an edge or not. So having the input image, we applying this Kenny edge algorithm, which can be easily used in OpenCV. As a result, we have a series of contours. We are taking only those closed contours, which will become our candidates, our region proposals. We are padding those region proposals with an amount of pixels. Why? Because we want to have a kind of context to our classifier. And then you see as a result, we have some parts of the screen. Those parts of the screen are actually our proposal, our candidates. Those proposals are actually the input to our convolutional neural network. So we feed those region proposals to our convolutional neural network, and then at the output we have the rectangles and the label associated with it. Of course, there might be some uncertainties. For example, for an icon, you are not sure whether it's a simple image there or it's a button. So in order to discriminate better, we are doing a second detection, but right now we are moving the mouse over that area which contains this uncertainty. And probably we'll find much more clear what is there. Of course, it is important to know exactly what is the content, what is the context for that particular control. For example, for a text box, it's important to know which is the content of this text box. And in order to do that, we are applying an OCR algorithm. And after that, as a result, what we have? We have the control, the rectangle. We have also the type of the control, and also the text, which can be the label or the context of the content of the text box. So that is our pipeline. We also have done a second approach, which right now is based on fast RCNN. So the single difference is that instead of using a convolutional neural network, we are using fast RCNN. The big advantage here is that we can have image with different sizes as an input. It's much more faster. It's much more efficient. The difference between the basic algorithm is the fact that in the Microsoft algorithm, they were talking about detector of a region proposal done using selective search, which is an implementation which deals with region proposals. But right now we are applying also the Kenny algorithm. What's the results? After we applied the first approach, so we came out with accuracy near 97%, of course, on our validation data. The model size was about 40 megabytes. We have implemented in both CNTK and TensorFlow. And it was relatively easy to train. The training took 1 day on a normal GPU. Now, I will talk also about the implementation side, which is very important. Actually, it's the core part. Okay, we have done the prototyping phase in Python, and the execution, consuming the model part in C#. Of course, one of the difficult issue was to choose the right deep frameworks. There are a lot of deep frameworks available. You know, there is TensorFlow, there is Theano, there is Caffe, there is Keras. So there are a lot of deep network frameworks available. There is also CNTK. But in our case, our applications, which we are trying to automate, are executing only in Windows. So from the beginning,